All right. Our next speaker is Diego Aineto. Over to you.
Thank you. So, hi everyone. My name is Diego, and this is a joint work with my colleague Enrico Scala. In this work, we look at the quality of solution policies for fund planning, which so far have been mainly studied in terms of the size of the policy. Instead, we want to look at them in terms of the number of actions or the cost of the actions that you need to take to reach the goal following these policies. So to motivate our approach, I'm going to present this example. This is a domain that we came up with. We call it the IC grid, and it's very much inspired by Frozen Lake from the OpenAI Gymnasium. So this is a grid wall where we have three types of tiles: frozen, frozen, obstacles, and holes. No? Frozen tiles, obstacles, and holes. And in order to navigate this grid, the agent can move into any adjacent tile. However, since the tiles are frozen, the agent might slip, moving two tiles instead of one. So depending on the type of this second tile, we have three different outcomes. In the first case, if the second tile is another frozen tile, the agent slips and falls and lands there. If it is a hole, the agent is going to fall in this hole and never get out. This is a dead end. And otherwise, if it is an obstacle, a wall, this wall is going to block the agent from slipping, and the agent lands in the intended position. For this particular example, we want to go from the horrible at pointing, I guess. We're going to go from the top left to the top right. And in order to do that, we need to cross one of these three corridors in the second to last column. So here we have three alternative policies that solve this task. And the question that we ask is, if we wanted to minimize the number of actions that you need to take to reach the goal, which one of these policies would you follow? And the answer is not obvious because it is going to depend on what happens at execution times, and this is a non-deterministic domain. So still, we can reason about this in a systematic way by looking at the extremes of the policy, that is the best case and the worst case. So the first policy is fully committed to the top corridor, which is also the shortest path. And in this case, if everything goes well, it will only require five actions in order to reach the goal. However, this is a very risky policy because in order to use that corridor, you need to align yourself with the corridor. And if you keep sleeping, moving two tiles instead of one, you are never going to do that. So in the worst case, you will never see the goal. Then we have the second policy, which also tries to go through this top corridor, but when the agent fails to align itself, it will switch to the middle one using those two obstacles there in the bottom left to align itself, and from there it can proceed smoothly. So this maintains the same best case at 5 and has a better worst case at 12. And then we have the last policy, which never tries to go for the top corridor and instead goes directly for the safest middle corridor. So in this case, we have a higher best case at 7 and a lower worst case at 11. So looking at the figures and looking, for example, first at the best case, we can see that the first and second policies are equally good. But when we consider the best and worst case together, we realize that the second policy is actually more balanced. And then we have the third policy, which is not really comparable to the other two because it's better in some regards and worse in others. So when you do this kind of reasoning, what you are actually doing is some sort of bi-objective optimization, and this is the reason why we decided to take this approach here. So the contributions of this work are twofold. On the formulation side, we present the bi-objective fund planning task. This is general for any pair of metrics. But then we instantiate this task with policy call metrics, in particular the best and the worst case that we saw in the example. Then for the method, at the method level, we present a new algorithm, BOA and star, which is an extension of an existing algorithm, and star. And since these two algorithms are A star style algorithms, we're going to also design some admissible heuristics for these algorithms and for the two metrics that we consider. Okay, so now for some essential background, we use the general formulation, the typical formulation for the fund planning task. We have a set of variables, a set of non-deterministic actions, an initial state, and a goal condition. And on top of that, we are also going to have a cost function that assigns to each action a positive cost in the way you do in classical planning. Then we say that a solution is a policy that maps states into actions. Then regarding the policy, we need to keep in mind a couple of concepts because we will use them later for the algorithm. The first one are the outgoing states, which are states that you can reach when you execute the policy in the initial state, but that are not yet covered. So the policy has not assigned an action to them yet. And these outgoing states are partitioned into goal and non-goal states. And then the second concept is the set of maximal trajectories that the policy induces when you execute it in the initial state. Then a solution policy is valid if it is closed and proper. Closed here means that there is no outgoing non-goal states. And proper means that from every reachable state, you can reach the goal following the policy. So the first thing that we do is to formulate the bi-objective fund planning task simply by adding a pair of metrics, Q1 and Q2, that we want to minimize. However, when you work with more than one metric, you will usually never find a single solution that minimizes both at the same time. So in bi-objective and general multi-objective optimization, you work with a weaker notion of optimality called Pareto optimality, which is defined through this notion of Pareto dominance. So Pareto dominance says that a policy dominates another if it is strictly better with respect to one metric and no worse with respect to the other. And then a Pareto optimal policy is one that is not dominated by any other solution. Then when you work with Pareto optimality, you will not only have multiple Pareto optimal solutions, but you might have multiple different costs that are optimal, which means that the solution to this bi-objective fund task is going to be a set of Pareto optimal solutions. If you consider all of them, you have a Pareto frontier. If you consider a subset that is cost unique, you have a Pareto coverage set, which is the notion of solution that we follow here. And what I just presented was general for any pair of metrics, but we are going to use policy cost metrics. The intuition here is that for each trajectory induced by the policy, you have a different cost. So we are going to use this cost as the building block for our metrics. The cost of a trajectory is simply defined as the sum of the actions that induce this particular trajectory. And then for the best and the worst case, we simply have to minimize or maximize overall the trajectories induced by the policy. Oops. Okay, so for the method, the algorithm that we present is an extension of an existing algorithm, an star, which was presented here at ICAPS a couple of years ago. This is an A-star style algorithm for policy space, meaning that we have an open list ordered by F values as usual, but the nodes in this open list are policies, not states. When we extract a policy, if this policy is closed and proper, it is a solution. If the F values are admissible, it is optimal. Otherwise, we have to expand the policy. And the expansion step here consists on choosing one of the states that are of the outgoing states, or the states that the policy has not assigned an action yet. And then for every applicable action, we generate a new policy by adding the corresponding assignment. In our extension, since we have a pair of metrics, we are going to have a pair of F values. And we are going to use the first one to order the open list and the second one to break ties. So we are using a lexicographic order. This ordering ensures that whenever we find a solution, no solution that we will see in the future, it will never be dominated by a solution that we see later in the future. So in order to be Pareto optimal, we only need to make sure that nothing that we saw before dominates this new solution. This means that, in principle, we only need to do a dominance check against the current solution set. However, there is a smarter way to do this that we can also use to do some pruning. The idea for this is that the solutions enter our solution set with increasing values of the first metric and decreasing values of the second metric. Therefore, the last solution that we added has minimal second-metric value. We can store this value, and we know that the next solution must have an even lower value than this. So whenever we extract as a policy from the open list, if this policy is equal or larger than this value that we are keeping track of, we know that that policy, if it is a solution, it is dominated already by the solution set. If it is not a solution, all the extensions of this policy will be dominated by the current solution set. And in this way, we can populate this Pareto coverage set iteratively. Now for the heuristics, this is just a quick glance. The intuition for these heuristics is that we are going to use admissible classical planning heuristics over the all-outcome determinization of the font task in order to design these heuristics. And then we formulate a number of them for the best and the worst case, including some blind heuristics just for completeness sake. In the paper, we prove admissibility and also dominant relationships. And we carried out some experiments, some evaluation studies to find the best configuration and verified that indeed it pays off to use the most informed heuristics here. Now for some empirical results. So we are first going to look at the quality of the solutions, which is the main point of this paper. And in this particular analysis, we are going to use &*, which is single objective, to optimize one of the metrics and look at the quality with respect to the second metric. So for instance, when we look at the best case, we ask &* to find the optimal solution for the worst case and compare the best case with respect to those solutions found by our bi-objective algorithm. And all those points below the diagonal are cases where our algorithm found solutions with a better best case. Similarly, when we do the opposite, so here in the right plot, we ask &* to optimize for the best case and evaluate the worst case. And all these dots here on the right are actually cyclic solutions where Bo &* was able to find a strong solution that had the same best case and obviously a much better worst case, since it is not cyclic. Then we also evaluated the coverage and runtime of the algorithm, and here we have a survival plot. The conclusion is that &*, so the single objective algorithm, is generally faster, but Bo &* is still competitive in terms of runtime, at least for these benchmarks that we evaluated it. So to conclude, we presented bi-objective font planning task and an algorithm for this task, Bo &*. Then we instantiated them with policy cost metrics and admissible heuristics for them in order to get cost-optimal solutions. And empirically, we saw that the solutions that we find with this bi-objective approach are better or at least more balanced than those found when optimizing for a single metric. As future directions, we would like to design better heuristics, and we are also considering doing a multi-objective extension of &*, so beyond 2 metrics. So that is all for my presentation. Thank you very much. If you're interested in the algorithm, please.
All right. Okay, lots of questions.
Hi, so you were talking about your policy cost metrics, which was looking at the minimum and maximum trajectory for a policy. You can have an exponential number of trajectories.
Yeah.
And so how do you actually compute these metrics?
Because you don't really have to compute all the trajectories. You can keep track.
Can you go to the mic?
Yeah. So the trick here is that the outgoing states are the terminal states of the trajectories. So you don't need to enumerate the trajectories. You only need to keep track of the outgoing states, which is much lower than the number of trajectories.
Hi.
Hi.
Thanks for your talk. I just had a similar question regarding the worst case heuristic, because as far as I know, you can go to a cycle and that worst case can be technically infinite.
Mm-hmm.
How do you compute this in practice, and Is this an edge case that is not considered?
So this is the cost of the worst case is mostly symbolic. You simply detect the cycle, and that value is going to be higher than whatever other finite cost you can find. No, it's an unbounded cost. So you can see it as a symbolic value that is higher than whatever other possible cost can be.
Okay, thank you, Diego. So let's see, if you will do fund planning, so in principle, so every strong policy, okay, will be sort of Pareto optimal in relation to any strong cyclic policy. But there may be strong cyclic policies, okay, that also Pareto optimal as well. So if there is a very good path in the best case, okay, it's going to be Pareto and so on. Is that correct?
So there is some observation here. No? So a strong cyclic policy can never dominate a strong policy. So if the solution admits strong policies, at least the Pareto frontier or the Pareto coefficient will have one strong policy.
Yes.
So the only possibility for a strong cyclic policy to be in the Pareto frontier is to have minimal best case. No?
Yeah. So, and of course, you don't compare with fund planners. Probably it's not going to work too well with fund benchmarks. If you try to do that, okay, in a sense, it should be looking for strong policies, if there are strong policies and things of that sort.
So we use benchmarks from SAT and PRP. And this works better when you have a strong policy, no?
Yes.
Not only strong cyclic policies, of course.
Mm-hmm. Okay.
But yeah, so there is a nice, I didn't go through this, but there is a nice correspondence between our quantitative taxonomy of policies and the usual quantitative taxonomy.
And among strong cyclic policies, let's say a problem that has no strong solutions. Among strong cyclic policies, is going to select one that has the best possible case, okay? Okay.
Yeah, so another thing is whether we can be more fine-grained with a strong cycle, not maybe how many cycles. I don't know which is better there. So
very good. Yeah. Thank you.
I had a question if no one else does. All right then. So I'm interested in your metrics. So it looks like, I mean, your metric is defined for a policy. And so I may have two policies on the Pareto frontier, which kind of, one does well on against some non-determinist, some environments, and it's those environments that the other one does badly. And in other words, your metrics only depend on the policy and some are aggregated across all environments. By environment, I mean resolutions of the non-determinism. Sorry, yeah, by environment, yeah, I'm looking at one planning problem, but these are non-deterministic domains, right? And so one can imagine that in one environment, let's call it, there's not much slippage, or there's only slippage in certain areas. And in another, it's always slipping all the time. And it seems that your metrics don't, I mean, they sort of aggregate across all of these. And it might be that you have two policies, both on the Pareto frontier, one, and you know, but they're good, their best metrics are good, but in different situations, in different environments, as I call it. And I'm wondering if you saw, well, if you had any comment on that.
So I'm not completely sure, but here we have that sort of situation, I guess. But so this is a single environment, but you have non-deterministic. So here we have a best case of 5, and here it's 7.
I think that meant that when the different environments have different scenarios that you can have.
So it's the same planning problem, just the resolutions of the non-determinism may be different. Okay, I'd love to talk to you afterwards and explain myself more clearly. Yeah, I think it's a difference in terminology.
Thank you for the talk. I wonder if you can say a little bit more about the properties that you need in your heuristics, so you get these results. Because it looked like if it's, for example, non-admissible, you might need to consider removing some of the solutions, or maybe I misunderstood that in the algorithm.
I can give you some more details about the heuristics. I didn't want to go into detail because it's a bit of a heretic. So I'm adopting and the Scala framework for heuristics. And here, when we talk about heuristics, we actually talk about values. Okay? And the reason for this is because when you want to define the heuristic for a policy, you cannot always do the separation of the G and the H value. So the heuristics that we define are combinations of two components. We have the cost of the trajectories, and from the terminal nodes, from the terminal state of these trajectories, we do a classical planning, an initial classical planning heuristic, SMART, then CAP, to estimate what is going to be the cheapest cost to the load. And depending on how you combine these two, you get different heuristics. So for example, you can minimize all of these costs and minimize all of these heuristic values, and you get one heuristic. And here, I think I have it here. Yeah, so this is the one. And this is the sum heuristic that we call, the sum of minimums. And here you can still see the G component and the H component. But you can do better than that by instead reasoning at the trajectory level, so you sum of these two elements at the trajectory level and do the mean over the mean. And here you don't have this distinction of the G and H component anymore. And this actually dominates the other. So I'm not sure if that was the answer. I just wanted to give you more details.
All right. This paper actually won the Best Paper Award, so we should congratulate Diego and Enrico on a wonderful paper as well as a wonderful talk.